Hi everyone! In this video we are going to discuss conjugate addition reactions, and this is actually going to be slightly different from our previous alpha carbon chemistry discussions. So let's just review conjugated systems. So let's say here we have two double bonds that are separated by a single bond. This would be considered a conjugated system. However, let's say those double bonds were separated by more than one single bond. That would be a non-conjugated system. And we have an sp3 carbon in the middle, which is what also tells us we have a non-conjugated system. Now we can also have non-carbon atoms in our conjugated system. So for example, we could have a carbonyl group that's separated from an alkene by one single bond. So that would also be a conjugated system. So we're really just looking for those pi electrons. And previously we learned that this is also called an alpha-beta unsaturated ketone. And we saw that we can form these alpha-beta unsaturated ketones through aldol condensation. Now let's say we move that double bond over one position. Now again we have a non-conjugated system. So it's really important that those double bonds are only separated by one single or sigma bond to give us that conjugated system. So let's look at some conjugate resonance forms, because this will tell us what types of reactions we can perform. All right, so let's start with that alpha-beta unsaturated ketone, and we're going to move pi electrons up to oxygen. So our first resonance structure shows that we have a negatively charged oxygen and a positively charged carbon at position 2. So let's just number these atoms. 1, 2, 3, 4. And then we can again move electrons over to create another resonance structure. And now, the positive charge is at position 4. So, knowing what we know about nucleophiles and electrophiles, where are the electrophilic positions on our alpha-beta unsaturated ketone? So the electrophilic positions are at carbon 2 and carbon 4. So we have two potential places where a nucleophile could attack. So a nucleophile could attack C2 or C4. So how do we know what's going to attack where? Well, strong and unstable nucleophiles will favor attack at C2. So remember, unstable or really strong nucleophiles would probably have a full negative charge, and it would be a concentrated negative charge, so it wouldn't be shared between two atoms, for instance, like we would see in a resonance structure. So this would be something like the hydroxide ion or an alkoxide ion, or maybe a Grignard reagent, for example. Now, what if we have a weak or stable nucleophile? Well, that will favor attack at carbon 4. Now, a stable nucleophile would be one where the negative charge is actually shared among multiple atoms. So likely that would have a resonance structure. So we'll just say that the nucleophile is resonance stabilized. And that's what makes it weak or stable. Let's see, stabilized. There we go. So let's look at an example. So let's prepare an alpha beta unsaturated aldehyde instead of a ketone. Once we have our alpha beta unsaturated aldehyde, then we're going to show how it would react with two different reagents, a strong nucleophile and then a weak nucleophile. So see if you can remember how to prepare that alpha beta unsaturated aldehyde. And remember, it has to do with aldol condensation. So feel free to pause the video, and when you're done, we'll go over it together. All right, so if you reviewed your notes on how to prepare that alpha beta unsaturated aldehyde, you'll know that we start with an aldehyde, and we'll just use a simple one here. And then we use base, and that will give us our beta hydroxyaldehyde. Then we're going to use heat to give us our alpha beta unsaturated aldehyde. And you could really use any aldehyde here, but remember we use that aldol condensation reaction. Okay, so now let's look at two different nucleophiles and how they would interact with this alpha beta unsaturated aldehyde. Okay, so the first reagent we'll use is a Grignard reagent. So remember, this is our strong nucleophile. So it's also unstable. So that means that it's going to attack carbon 2. So if we label our atoms here again, and then that will move electrons up to oxygen. Okay, so again, notice that that R group attacked the carbonyl carbon, which is actually more stable than carbon 4. Now, in the next step, the negatively charged oxygen is going to protonate itself. I'm just going to draw an arrow to water there. And we actually end up with an alcohol. In fact, this would be a secondary alcohol. So this is our 1,2 addition product. So you might remember from a long time ago, we talked about 1,2 addition versus 1,4 addition. Now, let's say instead of a strong and unstable nucleophile, we use something a little more stable. So let's use a Gilman reagent. So remember, this is an organocuprate molecule. It does pretty much the same thing that Grignard reagent would. It does have an R group that attacks. But in this case, because our reagent is weak and stable, reagent, it's actually going to attack carbon 4. So that's going to move electrons over one position. So our double bond is going to move over, and then electrons will go up to oxygen. All right. So now in the next step, oxygen is going to protonate itself. So we end up with an enol. And what do we know about enols? Do they last very long, or do they turn into something else? They turn into ketones, right? And there is some equilibrium there, so you will still have a small amount of enol, but it's not very much because the ketone is going to be favored. Okay, so looking at our final product, it kind of looks like we had a 1-2 addition, right? It kind of looks like we just added a hydrogen and an R group across that initial double bond. But looking at our intermediates, we can very much see that this is a 1,4 addition because we're adding hydrogen and the R group to the 1 and 4 positions if we number our atoms. So this is a 1,4 addition product, but because of that enol, we actually have a ketone that forms at the end, and that's what makes it look like we have a 1,2 addition, but it's actually 1,4 addition. So it gets kind of confusing sometimes. All right, so let's look at a very specific reaction called a Michael addition. So in a Michael addition, we have conjugate addition, just like we saw before, but this is going to be specifically 1,4 addition. And we're going to use a resonance stabilized nucleophile. Or a Gilman reagent. The Gilman reagent can also be used in this type of reaction. Okay, so let's look at an example of Michael addition. So we're going to start with a diketone or a dicarbonyl. And remember that if you have two carbonyl groups, the alpha carbon in the middle has very acidic protons because the conjugate base has two resonance structures, so it's extra stable. So we're just going to add a base that's going to leave electrons there behind to form an enolate. So this again is a resonance stabilized nucleophile or slash weak. Oops. Nucleophile. Okay, now remember that stable or weak nucleophiles are going to favor attacking carbon 4 on an alpha beta unsaturated ketone or aldehyde. So in the next step, let's just add one of those. We'll just do an alpha beta unsaturated ketone this time. So let's number our atoms that are involved in the conjugated system. And our enolate, again, will attack carbon 4 since it is weak and stable. That will move electrons over and up to oxygen. Okay, so now we have formed a bond with that carbon 4. So let's see, let's number our carbons again here. So we've got our atoms, 1, 2, 3, 4. So the new bond that we formed is right here in yellow. Okay. Now, looking back at our reaction using the Gilman reagent on the bottom, we saw that we end up with 1,4 addition, but we also see tautomerization to a ketone, which will kind of look like 1,2 addition. So one way that we could draw our arrows to indicate that we're ending up with that ketone at the end, we can show that the oxygen atom is going to reform its double bond. And then the actual double bond between carbons 2 and 3, we can show that they're going to, we're going to add a hydrogen there. It's just a little easier, and you kind of skip that tautomerization step to get to the product. But you can show the tautomerization too. That's totally fine. Okay, so we get back our ketone there. And that's it. So that is our final product. So really, if we look at what we started with, that's the big ring system. And if we look at the alpha-beta unsaturated ketone, we pretty much just added that whole thing onto the ring system and got rid of that double bond between carbons 3 and 4. But again, this will be 1,4 addition. So let's look at some common enolates that we would use in these types of reactions. And another name for these particular enolates, these weak and stable enolates, is we can call them Michael donors. So these are doubly stabilized enolates. So we've got those dicarbonyls. Although there are other forms as well that can be doubly stabilized through resonance. So some common ones would be, for instance, this diketone here that has a negative charge on its central carbon. We could also have diethyl malonate that we saw before. And we've just got a negative charge on that central carbon. We could also look at the ethyl, let's see, I'm forgetting the name. This would be used in the acetoacetic ester synthesis. So that could also act as a Michael donor. Or maybe we have a nitrile on one side and a ketone on the other. That could also be a Michael donor because there is resonance there on both sides. You could also have this kind of interesting molecule with a nitrogen. Whoa, my pen went bold on me. Let's see if I can draw that a little smaller. There we go. So we haven't really seen this type of molecule used as a nucleophile before, but this could also work as a Michael donor because there is resonance there. and there are a couple of resonance structures that we could form. And then last but not least is that Gilman reagent that we talked about. So this one isn't resonance stabilized, but it is a weak nucleophile because it is bulky. Okay. So I'll just put Gilman reagent here so we remember what that is. All right, and then common Michael acceptors, because whenever you have a donor, you usually have an acceptor. Michael acceptors would really be any type of conjugated system. So typically those will be our alpha, beta, unsaturated aldehydes or ketones. Your textbook does list a couple of others, but I think we're mostly just going to focus on those aldehydes and ketones that are unsaturated. So let's practice. So I'm going to give you a starting material. Okay, and this particular ketone here is going to first react with LDA. So remember, LDA is a bulky base that will turn our ketone into an enolate. Then we're going to react our enolate with this alpha beta unsaturated ketone. And then finally, we'll use acid at the end. Now, when we form our enolate with this ketone, it might not necessarily be as weak or stable as our doubly stabilized enolates, because notice we don't have two carbonyl groups, we only have one on our starting material. So most likely we're probably going to end up with two products. So one will involve 1,2 addition, the other will involve 1,4 addition. So see if you can figure out the two products that would form in this reaction. And then we'll go over which one would be the major product and which one would be the minor product. So feel free to pause the video and then we'll go over it together. All right, so let's start by showing what our enolate would look like. So we're going to add LDA, and we have two alpha carbons, but this molecule is symmetrical, so it doesn't really matter which side we take a proton from. So we'll form a negative charge on one of those alpha carbons. And in the next step, we're going to react that with our alpha beta unsaturated ketone. And let's just number our atoms that are in the conjugated system. So I mentioned that we could have either a 1,2 addition product or a 1,4 addition product. So let's use different colors of arrows to show both of our possible reactions. So I'll start with green arrows and let's show the 1,2 addition. So we'll show that the enolate or Michael donor, that wouldn't be a Michael donor, but we'll show that the enolate is attacking the carbonyl carbon, carbon 2, and that's going to give us, I'll draw it in green. All right. And let's just number those same atoms so we can kind of see how they added to our molecule or our enolate. So again, this is for 1,2 addition, and this is our intermediate. All right, now let's show the other one. I'll draw these arrows in orange. So what if our enolate attacks carbon 4? Again, that will move our double bond over, and then we'll move electrons up to oxygen. Okay, and let's number those atoms as well, just so we can see how they added to our enolate. Okay, so now we have to add acid as our last step to protonate our oxygen atoms. So if we protonate the green 1,2 addition product, we'll end up forming an alcohol at that position. And if we add, oh, sorry, I forgot to show that we're adding acid here. If we add acid to our 1,4 addition intermediate, we are going to end up with an enol, and then we said that that would tautomerize into a ketone. So we can just show that oxygen turning into a ketone. All right, so now we have to figure out what is our major product and our minor product. So normally we would look at our double bonds and our intermediates and see how substituted they are. But in this case, we're actually going to look at our enolate. Is it a weak and stable enolate, or is it a strong and unstable enolate? So remember, we said that Michael donors in particular are doubly stabilized enolates, and they'll result in 1,4 addition. But looking at our enolate, that only has one resonance structure because we only have one carbonyl group there. So this is actually a relatively unstable nucleophile. So that's probably going to mean that 1,2 addition is the major product. Because remember, unstable nucleophiles are going to attack carbon 2 over carbon 4. So our 1,2 addition product is the major product, and the 1,4 addition is the minor product. So we can't really rely on the stability of the intermediates in this case. All right. So I know that Michael reactions are a little confusing since we have to consider both how strong the nucleophile is, will it attack carbon 2, carbon 4? So definitely go over this section a couple times just to make sure you understand it. And if you do have any questions, just please let me know. In the next video, we're going to go over stork enamine synthesis.